Hello, this is Shreya with GeoBiz Technology. You may have already watched our intro video or our video on our standard capabilities, but if you have not, we are an acoustic log processing company. So we take the data collected by any service company's wireline or MWD tool, and we process that data to determine formation characteristics. The following slides are going to go over some of the unique capabilities we have with that data, and I hope you enjoy them. So the unique capabilities that I was referring to, they are our fracture identification from Sonic, and we also have a proprietary fast shear azimuth model to calculate a more accurate azimuth in a deviated wells, which we will go over in more depth later. But we also have the standard capabilities, which we define as your shear anisotropy or slowness or standard petrophysical analyses, but those things we went over in more depth in another video, which you are more than welcome to look at if you haven't already. These set of slides are just going to focus on the unique capabilities. So the first thing that we are going to go over is our fracture identification, which we are using sectored compressional data to do. This is a bar graph that was published in an SPE paper from June of 2011, and essentially what it is illustrating is that around 30% of perforations are not producing. This is not good. I think that what it really means is that this 30% of perforations are significantly contributing to your lifting costs while eating into margins. And to be fair, also, we were recently at a symposium and they estimated this number to be higher, but let's just stick with the 30%. So if 30% of the perforations are eating into your margins, I think the question becomes, how do we cut down that 30% so that we can increase profit margins on our wells and create a more effective completions plan? Furthermore, and some of these problems are more common in, let's say, a fractured carbonate formation, but I think some of them are applicable in all unconventionals. So in fractured formations, you see unusual or unpredicted water production or gas production, and the unnecessary completions cost could be these 30% that we were just talking about of perforations not producing, or it could also be acidizing costs or other related costs associated with completions that are problematic. And I think it has been well documented that fractures play an essential role in the control of flow, and so identifying these fractures can help create a completions plan that results in proper drainage, whether you are taking advantage of the naturally fractured zones or avoiding the naturally fractured zones. It's important to know where they are for an effective completions plan. And it can lead to avoidance of these unusual gas or water production in an otherwise oil-producing interval. And it can avoid acidizing or fracturing low permeability unfractured zones, so it can help reduce perforating or spending money on areas that aren't going to significantly contribute to your production. So, since fractures play a crucial role in controlling the flow, I think it follows that identifying these naturally fractured zones could help to create a more efficient completions plan and plan future well placement through field modeling more effectively. And there are current methodologies available to identify fractures. The Aguilera method, the DLL method, and other related methods, the issue with them is that they are essentially inferences and of limited local value. What do I mean by that? That means that they're not directly trying to identify fractures, they're measuring some other phenomenon and inferring that these phenomena imply a fracture zone. Shear anisotropy is probably one of the more common characterization methods from sonic currently, but I think it's important to note that it characterizes anisotropy and not fractures. Particularly in unconventionals, you often see that the formation is inherently anisotropic, and so in shear anisotropy processing, oftentimes the fractures that are apparent, it's difficult to distinguish the fractured zones from the inherent anisotropy present within the formation. And so the shear waves fail to split or demonstrate anything of use in these wells. Furthermore, you have the times when the fractured sections show anisotropy below the tool threshold, and in deviated wells you also see mathematical limitations that are imposed by the borehole and geometry around whether the wavelength necessary to perform the calculations, for instance, is able to be collected. Probably the most accurate method is to identify fractures is imaging. So, and it's great when it works, obviously, but with the prevalence of oil-based mud in unconventionals and also the presence of conductive deposits, it can lead to obscured image results and poor resolution. Furthermore, if you have a highly deviated well, there's often poor pad contact, which can also negatively affect your resolution in imaging. But we're not suggesting not to use these. It's just important to be aware of the limitations of these methods. And oftentimes, you spend a lot of time and money sending your imaging tool down into the wellbore, collect the data, and then you spend a lot of time and money to process that result, and oftentimes you're not getting that result until a month later, and that's when you find out that you have a poor resolution on it, and it just feels like a waste, and that's really unfortunate. And what we are suggesting could be an alternative. It's a lower cost and possibly faster alternative, but also could simply be a backup method so that you could verify your image result or have a backup if the resolution happens to be poor. So we're using we're providing a customized acoustic solution that's designed for the well. What we mean by that is not only do we have the proprietary methods for identifying natural fractured zones from the sonic data, but also we are choosing our frequency and bandwidths and tracking in time interactively so that the process result that we provide is true to the formation. And so once you get all of the processing methods, after using all of the processing methods, the plot that you receive provides a more complete interpretation of the well. Now, this is the theory behind our fracture identification method. Think of a table, and if you have a completely homogeneous table and you send a compressional wave through there, the compressional wave moves through the table in line with the particle motion, and the person at the other end of the table feels that same waveform, that present, the energy from it, just the same as where it started. However, on the other hand, if there was a big crack in the middle of the table, there would be a large drop in energy when traversing that crack. And the person at the other end of the table would feel a much more dampened energy. So the theory that we based our algorithms around are that compressional waves drop in energy when traversing a fracture. We're using raw, sectored compressional waveforms, and we process them, combine them, rotate them, and map them. And the importance of the sectored nature of the compressional waveforms is that we wanted an azimuthal calculation, so we can not only identify the location of these fractures, but also the direction. I think it's also important to note that what we are really mapping with the energy from the waveforms is an accumulation of stresses within the formation. So the stresses accumulate and they culminate in a fracture. So you're not necessarily going to see a single crack like you would in an image reflected within this processing method. You'll see the accumulation of stresses building up to the crack and then dissipating again. This is our workflow to kind of walk you through what it is that we're doing. So we start with the raw waveforms as stated. We can't do much with the last file, so we need the D-list tape. Now we mute the raw waveforms in the time domain, filter them in the frequency domain, and target and isolate the frequency spectrum of interest. So it would be a different frequency spectrum for compressional versus shear. And these first four may look familiar to you if you've already watched the standard capabilities slides, because it's essentially the same set of processing steps that we do for our shear anisotropy calculations. So then we stack the data arrays, and this is important for the compressional, for the fracture identification from compressional, because we're looking for fine perturbations in the data, and stacking, which is, we took inspiration from seismic and seismology for this processing algorithm in this part of it. It helps to amplify the anomalies that we are seeking. Then we normalize the arrays, and this is important to account for any differences around the wellbore, differences in lithology, or if a section has been caved in, or there's just something. Normalization helps to stabilize that waveform, stabilize the data, and account for any differences that may not be important to the final result. So we compute the RMS energy, rotate the RMS arrays, compute the RMS differential and the azimuth. We plot the RMS differential and the azimuth Rhodes diagrams. And then we deliver the electronic or paper plots with the last file, so the result looks very similar and very familiar to what you're used to receiving from acoustic processing already. And this is an example of what a plot would look like. So you have your caliper and gamma ray, then the resistivity, then the fracture identification from compressional. Then you have your Rhodes diagrams associated with the fracture density in the following track, your shear anisotropy result, the Rhodes diagram associated with the shear, and finally a closer look at the waveform. Next, we're going to look over some of the some case studies. So we've tested and used this in the Bakken, in the Permian Basin, in Eagleford, and in a few international fields. So the two examples that we are going to go over were blind tests in the Permian and in Eagleford. We've used this extensively in laterals, and in laterals or in highly or more deviated wells, we don't necessarily need specifically sectored compressional data. We can use cross-dipole waveform data in laterals because we are taking advantage of a phenomenon by the name of leaky mode, which simulates a compressional wavefront. It's also important to note that in essence, we're looking for fractured zones instead of individual fractures. Individual sort of anomalies or singularities within the data, they can be induced fractures, they can be hairline fractures, or they could simply be weaknesses within the formation. I think it becomes a little more iffy as to what it is. I mean, we do see these things, but it becomes much more of an interpretation. I don't want to say iffy, but more of an interpretation. Whereas the fractured zones become apparent as a highly active section of the data, so it's much clearer. And they're usually where what natural fractures become apparent as is these fractured zones. We found in these blind tests about an 80 to 85% correlation with core over fractured and unfractured zones. So this was a blind test against core in the Eagleford. This was the full plot. On the left-hand side is the gamma ray. In the middle is our fracture identification. Then on the far right is the shear anisotropy. We did not calculate the shear anisotropy. That was calculated by a third party. We also did not have access to the core data until after we provided our fracture identification result. Here's a closer look at it because I know plots are somewhat awkward to look at. The red X's that you're seeing, they are the baseline. Where they're in a straight line, that's the baseline. There are no fractures there. Where the X's deviate from that baseline, that is where fractures were seen within the core. And the more the X's deviate from the baseline, the more or the higher intensity or the more dense the fractures were within that section of the core. And over the length of the well, we saw here about an 85% correlation. This is again a little bit of a closer look at the plot. As you can see with the shear anisotropy result, what should happen is that the shear waves should split when encountering a fracture. However, as you can see, they do not. There was very little splitting, and the splitting that did occur was somewhat random, and so it's hard to say that it correlated with the fractures in any way. So as you can see in this example, the fracture identification method provided a much clearer picture of what was happening within the well bore than the shear anisotropy result. This next example is from the Permian. We split it up into 3 sections, but it's all from the same well. So in this portion of the well, we would say that there was little to no fractures, at all within this portion of the well bore. And this was a blind test as well. So we provided this result, and then we received the image result. So once we got the image, we saw that it correlated with what we identified as an area with no fractures. So this is a little bit further down the well, and we, at the top of this section, you can see that there is a singularity. And so we thought that this would be a hairline fracture or an induced fracture, or some weakness within the formation. And so when we received the image result, we saw that it was, in fact, what the operator said was an induced fracture. So it picked that up quite well. Next, and further down in the well, this was towards the bottom of the well, and we saw this to be, or we interpreted this as a heavily fractured zone. So as you can see, there's much more activity within this zone. And when we received the image result, sure enough, that correlated with what we had originally found, and it was a heavily fractured zone within the well. So some of our conclusions from the case studies that we did and just in general was that the identification of fractured zones helps to find flow paths. Whether you want to exploit them or avoid them, it does help to find these flow paths. The standard methodology has some limitations, much like we saw in Eagleford with the shear anisotropy. The shear waves not splitting when encountering fractures versus the fracture identification method picking up those areas with pretty good accuracy that were fractured. And these limitations just become more apparent in unconventionals and carbonates, mostly because most of the standard methodology was created with conventional wells in mind. And using this fracture identification, it helps to provide a backup to other methods that you may already be using and have implemented as part of your standard plans. It helps to create a more effective completions plan, especially if we can provide this information to you in a more timely manner than maybe you would receive other processing method data. And it can help with future well planning and placement. So next we're going to very quickly go over our fast shear azimuth modeling. So we were doing quite a lot of research about shear anisotropy, the current methods, about Alford, about just in general, trying to figure out this fracture identification technique and overcoming some of the problems that we saw with current methodologies. And what we came across was that even in Alford's original paper and in other, well documented in other papers as well, is that these calculations were based on vertical wells. And the trigonometric premise limited the calculations for when we translated this information into a horizontal or highly deviated well. And what's also well documented is that above 20 degrees from the vertical, error is introduced into these Alford-based azimuth calculations. Now, in reality, even though we're calling them shear waves and compressional waves, what's really being used by these tools are flexural waves. And so we were reading some papers about research conducted in seismology in the mantle on flexural waves, and we wanted to try to adopt them to our own analyses. And in the end, we used that information to create a calibrated correction factor based on flexural waveform theory to correct for the errors introduced by deviating from the vertical. And what we found by looking through a lot of our old data was that errors of around 20 degrees in azimuth calculations in wells with greater than 50-degree deviation while using a standard methodology. And a lot of wells have a greater than 50-degree deviation nowadays. So this was an example from our archives with an image result. So we used the image breakout as a baseline to compare whether our stress direction was correct or not. The original azimuth that was calculated using an Alford-based azimuth calculation was 34 degrees, and we recalculated that as well, got the same thing, 34 degrees, which is quite different and quite a ways off from the 11-degree stress direction from the image. Once we applied our calibrated correction factor, we got 14 degrees. It's not exactly the same, but it is definitely a lot closer and true to the formation than what was originally calculated using an Alford-based calculation. And just so you know, this particular well had about a 65-degree deviation from the vertical. So, how do you actually use all this really great data that you've collected and now processed in any sort of meaningful way? So you can use it to inform your completions plan. You can use it to refine your reservoir model or other geophysics models, or you can use it to create a field model. For us in particular, we have access to a field modeling approach that was developed by Texas A&M using a dual porosity model, and what it is essentially doing is it is inferring the fracture network across the field to calculate a drainage volume. And so it uses our fracture identification method as an input. It didn't always. Prior to being introduced to GeoBiz Technologies processing, and even still currently in other calculations, they're using microseismic data to find these natural fracture patterns or to try to get away from a standardized completions plan. But they did find problems with using the microseismic data. So using the fracture identification that we can provide, they could create a more realistic model to provide a drainage efficiency that's more reflective of the field. And that's it. That's an in-depth look at our unique capabilities. And feel free to ask any questions. Look at our unique capabilities. And feel free to ask any questions.